who are still here. This is the last session, and it's packed with exciting talks like, you want to upgrade what? Take it away.
Yeah. Hey, everyone. I'm Patrick, and I'm joined here by Nadia and Dimitri. We are all working on OvenK. Dimitri works on it from time to time to fix bugs. And today, we want to share a journey where, as you all know, every project acquires tech debt. And in OvenK, this is not exception, especially when we oftentimes want to move very fast, introduce features yesterday, and we cannot wait for native solutions. So we want to share a story how we ended up with a solution that caused us a lot of headaches, then how we fixed it, and most interestingly, how we made it so you can upgrade from one to the other without any disruption. So yeah, I won't go into the detail here. It's just what OvenK is, and you already know what it is. Just to reiterate, for the purposes of this talk, Oven Kubernetes runs OvenIC. We do not run OvenIC controller. So we do this all by ourselves. So every node has NBDB, SBDB, and all that. And we do the work that OvenIC controller would do. And here on the right-hand side, you can just see how we translate Kubernetes constructs and concepts into Oven. And yeah, same here. Surya already spoke about what a user-defined network is. Just a quick recap. It provides isolation. So it means you can have overlapping IPs between the networks. The networks are isolated between each other, but you can communicate across nodes within the same network. And what we did with primary EDNs is you can also do egress to outside. These are the types of the networks we support. So in layer 3, you would have a subnet per node. In layer 2, it's a flat network stretched across all nodes. And local net is a special type of a layer 2 where you connect to the underlay through separate physical connections and not use the default network interface. So yeah, today we are going to focus on L2 and the issues we had with it. This is a very simplified view of how it looked like in the legacy implementation. So all our pods between the nodes are connected to a distributed switch. Back in the day, there were no gateway routers. There was no external connectivity, so it was just overlay and east-west. We quickly had to add the top part. So what we ended up doing is we've introduced a gateway router to each node. And what we ended with is that each gateway router has the exact same IP address, but they do not have the same MAC address. So it was sort of a workaround to get our thing working, and we had to do a lot of tricks to make that happen. One important use case for layer 2 networks is virtual machines. And with KubeVirt, how it works is every VM runs inside a pod. So from our perspective, from the perspective of OvenK and Oven, a VM is just another pod. So we are not really aware of the VM workload. We do not configure anything inside of the guest. The VM is represented as a pod for us. As you may know, a major requirement for virtual machines is live migration. So you have to keep the state unchanged between the nodes when the VM migrates. You have to keep the same addresses. You have to ideally keep the connectivity, and something like a gateway cannot change. But in Kubernetes, pods do not migrate. You cannot move one pod from one node to the other. There is some talk upstream about making this possible, but it's not there yet. So what could go wrong? Like, pods cannot migrate. We configure them on specific nodes, and we want to allow VMs to migrate with the exact same network identity. The first issue we quickly found with our legacy implementation is that if we move the VM and also recreate a pod on a different node, then the gateway MAC, as I said, changes. But the VM is not aware. We are not directly configuring anything in the guest. So our workaround was to just send garp from OpenK. So if a VM migrates, the new node will garp, and hopefully the VM will learn the new MAC address. And of course, this isn't ideal. It worked, but this is something that is easily broken by a drop rule, by a lost packet, etc. And the very same thing gets even worse with IPv6. So arrays, every gateway router sent an array, which meant we have a multipath for default routing. And if a VM migrates and one of the nodes becomes unavailable, we still have the broken path in the routing of the VM. So it was really bad, and we didn't want to send the traffic to different nodes than the one that were hosting the VM, actually. So what we ended up doing is blocking external arrays with IP tables. That's because Oven doesn't allow you to block arrays. ACLs won't block array traffic, and this is just something that we had to do, and we don't like it. And of course, to change the gateways, we sent unsolicited arrays, so similar to before. Now, the list doesn't end there. The huge maintenance burden of us having to reconsider every feature specifically for this workaround layer 2 implementation. Egress IP had to have dependencies on something like external gateway IP being available, and a new feature that Surya spoke about of connecting UDNs was pretty much impossible without changes to the infrastructure or to the design of the network. So I'll give it to Nadia to explain how we fix it all and how it works.
Okay, so you could ask, why didn't you do that right on the first try? Well, that's because this nice feature of transit router wasn't available when we needed that, and thank you to everyone who made it available now. So what we needed is basically an extra router which would make lots of routing decisions, but without the transit router, all you end up with is just one router per node, which doesn't make much sense. You just have two routers now, doesn't solve any of the problems Patrick mentioned. And with the transit router, that makes much more sense. So VMs are more happy now because that transit router has the same IP on all the nodes and the same MAC address. So the default gateway for all VMs is the same, no matter on which node they end up. So no extra router advertisements or anything, trying to clean all that all up. And to mention the maintenance burden, we have multiple topology types, and you can see on the left side the layer 3 topology that looks like this. And the layer 2, the previous one, was like kind of broken, so we have to adjust all the features that should work on both these topologies. And now you can see the topologies are much more similar in terms of you have like the same switch and same router. Well, you can match the colors. So we are also more happy now because we can get rid of all the ugly hacks we had to implement for basically every single feature, moving all the stuff that was done on the cluster router to the gateway router because transit router didn't exist. Now, we don't want to support both the old layer 2 and new layer 2 topologies forever, so that would be nice to migrate all the existing clusters to the new topology, which is all nice as you now understand. Now the problem is we already have running clusters with running workloads using the old topology, so no disruption is allowed. And as you can imagine, you can't just go and like rewire all the routers live and hope it will work. But fortunately, or unfortunately, we have a Kubernetes upgrade process. So Kubernetes clusters have to upgrade from time to time. And how it happens is called a rolling upgrade, which means that every node that's about to be upgraded, all the workloads running on it will be migrated to the other nodes. Then this node will include like reboot, services, restarts, all you need to do. So nothing is running there. And then the pods will come back to allow the next nodes to be upgraded. So that's a perfect timing for us to do our rewiring too, without any disruption. Now, as Dumitru will talk you through that more, there is an upgrade topology that obviously won't just simply work. So we had to go through a lot of Slack conversations and problems to make it actually work. And we wanted to thank all the participants. That included a lot of people being involved in actually making this work. So we want to thank you all. And just to begin this upgrade path, that's what we have. The whole upgrade point is you have at the same time new topology and the old topology, because all nodes can be upgraded at the same time, and you need to make sure it works at the same time with pods running on both ones. The limitation here is the old topology runs the old version of your code, so you can't do anything on this side. You can only change things to make it work on the new node side.
So yeah, thanks Nadia and Patrick. That essentially means we need to ensure that the traffic flow on the interconnect between the upgraded node and the not yet upgraded node makes sense for the old version of the topology. So let's try to do that. So we have the same picture again. What we're stand here so I can point. What we're going to try to simulate is traffic coming from outside the cluster, entering the cluster through the new node, through the node that was upgraded to the new topology, crossing the interconnect. Oh, it hits a load balancer here. It hits a Kubernetes service that essentially denats the packet so that it goes to a backend that's on a pod running on the not yet upgraded nodes. So if we walk that through, this is our packet entering the node. The original source IP doesn't really matter. It's somewhere outside. Destination is that of the node, because this is a node port service. It's just a load balancer that does DNAT from our perspective. And at that point, the new topology is configured to DNAT. So it will select the backend of that service, which in our case, it happens to be pod 2 on the right side. So that's the IP there. And in order to ensure that reply traffic comes on the same path, it also SNATs to this internal IP here, 188.0.5. That's a special subnet that OVNK uses. All good. Then we hit this other router here, where we're going to route towards the pod IP, towards 203.203.0.3. And we also change the source MAC address because this is a router. So when you route, you need to change the source MAC address and decrement TTL and other stuff. And that's fine because our destination at that point is the pod 2 MAC. And this switch here is a distributed switch, and it knows that pod 2 exists across the interconnect, so it will just send the packet to the correct logical switch port that links to our pod. So it looks good until now. It's promising. Hopefully it keeps working. Now the pod needs to reply, and it already breaks because the pod needs to access an IP that's outside from its perspective, right? It needs to access this IP, 188.0.5. So that means it's going to use its default gateway. But the default gateway is the 203.203.0.1 here with MAC address ending in 3, right? Which doesn't match the MAC address we had on other nodes, but we'll see later. So it sends the packet up to its default gateway, but this default gateway has no clue how to reach that internal OVNK IP. So it uses its own default gateway and sends it out to the fabric. So we already are on the wrong path, and that doesn't work. So first hack. We thought, okay, the old node has this IP here, 165.0.3. That's called a join subnet in OVNK. It doesn't really matter. It's an internal subnet that we use for ensuring the traffic comes back on the same path. We don't really need it in the new topology, but in order to make this traffic work, let's just add it again. So we're essentially reverting some of the upgrade now. And we should also make sure that the MAC address is the one the node would have had in the not upgraded topology. So now if we run the original packet again, the difference is instead of SNATing to 188, we're going to SNAT to this 165 IP. Then we route, packet reaches the pod. Now the reply has destination 165.0.2, which is, so it goes to the default gateway, and the default gateway has an IP in that subnet, luckily, so it will send it back down after routing with destination IP 165.0.2 which is a known IP and a MAC address on the transit switch. So the transit switch sends it to the interconnect, and then it breaks again. Because we didn't really need this port in the new topology. So we said, okay, let's revert some more. So we re-added a similar logical switch port as we had in the legacy topology that needs to have the same tunnel key on both sides. So it needs to match the metadata that is going to be embedded in the Genève packet here. Otherwise, we're just going to drop the packet. And we also need to connect it to the router. So at this point, we're connecting the switch on the bottom with the router at the top with two links. We also need to make sure that the MAC address this guy has here is the same MAC address that we had on the gateway router before upgrade. So now we're also duplicating this MAC. It's not a huge problem, it's just weird. So okay, let's send the packet again. Now it gets on this side after the interconnect. This version of the transit switch knows how to send the packet further, so it sends it up to the router. We're already further, that's good. But the destination is 165.02, and this router, oh crap, we forgot to add a route. So we needed to add a static route, saying everything that's destined to this old IP that we don't really need, just send it up to the gateway route. So now, if we try, we hit the route, and we finally manage to unnat and send to the fabric. So the connection is established eventually. It took us only 4 tries. Nice. And then, oh yeah, no, sorry, the other way. So this was traffic entering node 1, an upgraded node going to a pod that's on a not yet upgraded node. What about the other direction? Hopefully it will just work, because we fixed a lot of issues already. Let's see. So traffic enters the old node. It's kind of similar to the previous case, right? It's destined to a load balancer here that's going to DNAT to the pod IP, but this time is the pod on the left. It's also going to SNAT to the 165.03 IP so that our replies come back on the same path. We send it down to the switch. The switch knows how to reach 203.203.02, knows the MAC address. That's pod 1 MAC. So it sends it to the interconnect. Yes, it worked. Now replies. Same story here. The pod uses the default gateway because the destination IP is somewhere outside its network. The default gateway is this one now. And this one has no route for 165.03, the old one. So we said, okay, we actually need to simulate what was going on in the previous topology. So we need an IP from that joint subnet to be configured on this, let's call it layer 2 switch upgrade hack port, right? So we just chose a fixed IP that we use on all upgraded nodes. Before that, we only had the MAC address, right? Now we also have the IP. So if you replay the reply, it goes to the default gateway. Destination IP is 165.03. So because the router has a connected route, it should just use that connected route and send the traffic back down. So in theory, we have a route match. And then it should go to the fabric, but it doesn't. We don't see the packet there. What the hell is going on? So then at that point, quite a few people came to us, to OVN folks, saying, hey, we have a connected route for this destination. It should match, but it didn't. How come the packet didn't make it to the other side? So after some digging, I replied with read the manual, please. The idea was the pod subnet was a /24. And that router there happened to have a sort of default route, policy source route, so matching on the source IP, sending all the traffic from this subnet up to the gateway router, which was bypassing our connected route essentially, because our connected route was a /16. And if you look at OVN, we do a longest prefix match, and 16 is shorter than 24, so we were preferring this first one. So then, I don't remember exactly who it was, probably one of these guys here. They said, let's add a funny route. So if you look at this route, it looks really weird. We have 165.03 via 165.03. That makes no sense, right? Well, it actually does, because it's a host route, so it has a very long prefix. the longest prefix. So we're going to match on this one. And at that point, OVN is going to try to figure out the interface that you need to use to reach the next hop. And it's going to select that, let's call it layer 2 upgrade port hack interface. So back to our topology, we have this new route here. We hit it now. We actually send the traffic down through this upgrade port, gets finally on this side, and back up to the fabric. This time it was better, only 3 tries. Yeah, that's about it on the traffic side. I'll let Nadia conclude.
Okay, so that wasn't even the full list of hacks, by the way, just the most fun ones. So the conclusions is non-disruptive topology upgrades are hard, but possible. And then designing a perfect network from day one is also generally hard, but also not always possible. And priorities and timelines always lead us to fun, obvious OVN-conf talks, as you have probably noticed. Yeah, and OVN was flexible enough to implement all the workarounds needed. So if you try to do maybe all the same things in the normal networking, I don't know if that's going to succeed, but OVN is good enough. So we are really happy with that. And just to conclude all that, eventually, when all nodes upgrade, you have the brand new topology on all the nodes, which looks something like that, with some tiny leftovers that we had to, from the reverted previous topology that we had to leave there, but still pretty enough. Yeah, and one more special thanks to Kiki, who couldn't join us today, but did a huge amount of work for this project, including starting this off, writing the enhancement for that, making a huge POC, just trying to prove that it's going to work, helping with all the VM-related hacks. So Kiki, if you're somewhere online, thank you. And that's it. Thank you for your attention, and I think we can take some questions.
Any questions? Come on.
Very clear.
Easy.
Easy.
So is there a final phase where you remove all the hacks?
Yes. Well, not all the hacks, really. There is a way to do that, following the exact same thing. So you can't get rid of that join IP that we had to add, the fake one from the previous topology. You can't just remove that because all the nodes are using that for the existing traffic. So the only way to do that is wait for the next upgrade cycle until all pods are drained, change all your SNATs on the node to the new one, and then remove the old IP. We have that as a maybe to do. Also, if you ask how much of the previous ugly hacks from the old topology we removed, the answer is none, because you need to keep them for this release, because we need to keep running the old node still to be consistent with that one. But hopefully a lot of cleanup will happen in the next release, basically.
So we can look forward to a version, another edition of this talk.
Yes.
Let's hope not.
Any other questions? Okay, let's thank our speakers one more time.
So